Hey everyone, welcome to this explainer. Today, we're diving straight into a massive operational shift that is completely rewiring software delivery right now. For years, we've kind of treated AI in software development as this hyper-competent assistant, right? A tool that sits right there in our IDE waiting for our explicit instructions. But what happens when that assistant literally doesn't need us to hold its hand anymore? Well, that's exactly what we're unpacking today. The huge paradigm shift from interactive, session-based AI coding assistants to persistent, autonomous background agents.
Now just take a look at that massive number on the screen, 500%. Yeah, you heard that right. That is the actual increase in landed pull requests that OpenAI teams saw within mere weeks of using a brand new method to manage their code bases. Guys, that's a 5-fold increase in tangible output. It's a staggering surge, and honestly, it gives us a really compelling reason to care about the technical weeds we're about to get into, because this represents a fundamental change in engineering throughput.
Okay, here is the roadmap for today, as we unpack all of this. We'll start off with the human attention bottleneck, introduce the new Symphony architecture, look at its distributed systems design, lock down the security implications, and finally, prep for what we're calling the new proof-of-work era. All right, Section 1, the human attention bottleneck. Let me start us off with a rhetorical question. How many AI chat tabs do you currently have open right now? And are you starting to feel the cognitive plateau of supervising all of them? The reality is, right now, developers are pretty much hard-capped at 3 to 5 simultaneous active tasks. It's just human attention limits. Think about it. When you try to run parallel sessions using tools like Cursor or Codex, you hit a structural ceiling. The bottleneck isn't the capability of the large language model. Actually, scratch that. The bottleneck is you. The cognitive overhead of constantly context switching, refining prompts, and manually approving tools, it eventually just tanks your net velocity. But as we compare on this slide, the Symphony orchestrated model removes that human bottleneck entirely. It scales to hundreds of concurrent agents, literally limited only by available compute power.
Moving right along to Section 2, enter OpenAI Symphony. So what exactly is this new paradigm that's flipping the economics of code changes on its head?
First things first, we absolutely need to distinguish OpenAI Symphony from another project with a very similar name. OpenAI Symphony is a back-end automation specification written in Elixir. It's a non-interactive, code-level execution daemon. Do not confuse this with the academic framework OS Symphony, which is a multimodal computer use agent built to visually click around graphical desktops like Windows or Mac OS. OpenAI Symphony? It operates entirely out of sight, completely headless. So how does it actually work? Well, Symphony turns your existing issue tracker into the primary control plane for these autonomous coding agents. Instead of you playing typist and babysitting a chatbot session, Symphony continuously pulls your project board, say linear for instance. Your job shifts completely to asynchronous work management. To put that into perspective, during internal trials, an OpenAI engineer actually initiated and landed 3 major code modifications from a mobile issue tracker app while sitting in a remote cabin with terrible Wi-Fi. The orchestration service handled all the compiling, the environment cloning, the testing, the whole shebang. The human literally just had to tap merge. Section 3, built for distributed systems. To understand why this actually works reliably at scale, we really need to peel back a layer and look at the architectural decisions. If you look at this table comparing popular multi-agent frameworks, you'll see a stark contrast. Conversational Python-based setups are great for prototyping, but they really struggle over long horizons with fault tolerance. Symphony avoids this entirely by leveraging the Elixir and Erlang OTP runtime. Why? Because managing dozens of concurrent agents running hour-long tasks is essentially a distributed systems problem. Process crashes and API timeouts are guaranteed. Symphony handles this with native system-level fault tolerance, meaning if an agent crashes, it just cleanly restarts without taking down your entire system. And that robust architecture feeds right into a ruthlessly efficient task management system. Here we can see Symphony's coordination layer, which manages a super strict 5-state lifecycle machine to prevent race conditions and duplicate tasks. Issues sit as unclaimed. When picked up, they're claimed to reserve the slot, then transition to running. If it hits a snag, it goes to retry queued. And finally, upon success, it's released to free up resources. Clean, strict, and highly organized.
Now, check out the math brilliantly illustrated here. During that retry queued state we just mentioned, the orchestrator relies on an exponential backoff formula. It basically ensures continuous execution even when API timeouts or process crashes happen. The system doesn't just throw its hands up and bother you. It patiently calculates its retry window and goes right back to work on its own.
Because Symphony operates as a persistent daemon, maintaining continuous, stateful connections, traditional serverless architectures just won't cut it. Instead, it utilizes platforms like Upstash Box for cloud sandbox environments that actually preserve file systems between runs. And deployment is a breeze. You just run the npx Symphony Box command, and you are off to the races.
Moving to Section 4, Security and Autonomous Agents. Obviously, peeling back one more layer, granting autonomous workers the power to modify file systems and run shell commands requires extremely strict isolation.
To defend against things like prompt injection or malicious third-party code, Symphony operates with secure-by-default configurations across 3 distinct sandboxing levels. You've got Workspace Write as the default, which strictly isolates any file modifications to the active issues folder. You can dial that down to read-only for diagnostic stuff, or crank it all the way up to danger full access if you legitimately need unrestricted administrative access.
Finally, Section 5, the Proof of Work era. This secure, highly scalable infrastructure brings us to the ultimate shift in our daily jobs as developers. The interaction model has completely decoupled. You aren't guiding the AI anymore. The autonomous agent's sole new goal is to act as a black box implementation runner and convince you, the manager, to merge its code. The psychological burden of actually writing the implementation totally lifted.
But, how does a black box agent actually convince you? Well, it submits an indisputable proof of work bundle. It's not just a block of code. We're talking continuous integration validation to verify correctness, automated complexity analysis, actual recorded workspace walkthrough videos so you can watch the code work in a sandbox, and interactive code review comments explaining its choices. Now, because human effort is removed from implementation, that massive 500% surge of pull requests we talked about at the start, it's all going to hit the review stage. Platform teams have to shift their focus to harness engineering and start monitoring these new metrics. You're no longer measuring lines of code. You're measuring lead time to usable functionality, defect escape rates, and peer review friction.
So, the crucial point we want to leave you with today. Are your internal testing pipelines and issue trackers robust enough for you to embrace this paradigm shift? Because if your automated test suites are flaky today, they will absolutely buckle under the weight of hundreds of autonomous pull requests tomorrow. The agents are ready to do the work. The question is, are you ready to manage them?